Multivariate regressions extend the single variable setting we've considered so far. It is reasonable to expect that, by considering more variables in the regression equation, we'll improve its explanatory power and provide a better idea of the full picture of circumstances that determine the development of the variable we are trying to predict. Think of the example we provided before: house prices. When a buyer acquires a house, he usually wants to understand everything about the property. He is interested in the house's size, but he's also interested in its location, number of rooms, current condition, proximity to good schools and transportation, the neighbors living close by, and so on. All these factors play a role and affect pricing. Therefore, a regression that considers multiple variables should provide predictions closer to true results. The main catch is we need the right variables. Otherwise, results could be misleading. Once we are familiar with how simple regressions function, as we already are, we can easily understand multiple regressions. The form of the regression equation is almost the same, with the slight difference that we have multiple beta coefficients and explanatory variables. It is up to the analyst's discretion to choose how many explanatory variables will be included. If their number is higher than 1, we can talk about a multiple regression. The principle according to which the regression is calculated is the same as in the simple regression setting. We are estimating a best-fitting line minimizing the sum of squared residuals. It is more difficult to represent the best-fitting line on a plot, given we are calculating its fit through multiple dimensions. If the independent variables are more than 2, things become complicated. If they are 3, you can use a sophisticated three-dimensional graph. But have you seen a graph with 4 or more dimensions? At least, I haven't, to be honest. But to understand how the regression coefficients are obtained, try to imagine the software you are using knows how to calculate the equation of a best-fitting line in 4, 5, 6, or more dimensions. Mathematic formulas make this a possible task. Similar to what we saw before, the R-squared measurement will help us determine how powerful the regression we've obtained is. Again, R-squared can be from 0 to 1, and the more variables we include in the equation, the higher we would expect it to be. There are 2 main ways to check if an explanatory variable is helpful. First, we can run a regression with the variable, and then run a new regression without that variable, or with a different variable. We should observe how R-squared changes. If it is higher the first time, then this independent variable has good explanatory power, and its value contributes to the explanation of the value of the dependent variable. The other mechanism at our disposal is the p-values of the beta coefficients. A p-value in statistics is the probability to obtain a result that is more extreme than the one we've obtained. So, in this case, this is the probability that the beta coefficients we've estimated should have been different. So, a low p-value is a good thing. It provides assurance that the real beta coefficient differs from 0 and helps us explain the dependent variable. A p-value that is lower than 5% allows us to state we can be 95% confident that the beta coefficient we've estimated is different than 0. Practitioners accept p-values that are lower than 5%, or if more conservative, lower than 1%. This is how we can run a multivariate regression. Please know that the beta coefficients estimated in a multivariate regression can still be interpreted as the marginal impact that an explanatory variable has on the dependent variable. But this is only true if all other explanatory variables remain constant. So, If we've obtained a regression that shows how a stock's expected return is a function of the country's GDP growth and the industry growth rate, and we've obtained a 0.8 beta coefficient for GDP growth and a 1.2 beta coefficient for industry growth, we can say that for every percentage increase of GDP growth, the company will be expected to earn 0.8% more if the expected industry growth remains the same. The expected return and the GDP growth are interrelated in this regression, and we cannot interpret one without the other. All right, that's excellent. Now that you know what a multiple regression is, we would like to show you how to calculate it in Python. Have fun with our next lessons, and thanks for watching.